Hello there. This video is going to talk about quadratic functions and their graphs. And so we'll just run through some preliminary information and then we'll kind of apply that. And we'll look at different ways that we can talk about the parts of a quadratic graph. There are two formats that we can see a function represented, a quadratic function represented. The first one is called the general form. This is the one where we have ax squared plus bx plus c. The second one is called the vertex form. This one's been factored, and that can be a benefit to us. It's called the vertex form for a reason. It gives us a big hint on what the vertex is. Both of these, if we were to expand them out, would include an x squared, and that is what makes the function quadratic. It's also what makes the graph shape turn out to be a parabola. We're talking about parabolas today. Our goal is to start to take the equation and connect it to what we see in the graph. So we'll start with the a. The a part of the equation is actually the same in both formats. Here and here is the same. And it's represented by the same number, even if we convert between one format to the other. So if the number for a is positive or bigger than 0, then we're going to see a parabola that opens up. If the number part for a is, or the value for a is less than 0 or negative, that's when we see that the parabola is reflected over the x-axis, and so it opens down. Okay. Then we're going to add in, so all of this is very much connected to the transformation ideas that we've talked about in previous chapters. So for the next two here, if the value for a, and we put the absolute value bars here just to remove the sign, because at this point we're not really talking about the positive or negative sign that's addressed up here. We're just talking about the number part of a. So if the number part of a, disregarding the sign, is bigger than 1, so that could be 2, that could be -2. The number part is bigger than 1. Then we're going to have a parabola that is narrow and tall and skinny. And that is because it's been vertically stretched. Okay, likewise, if the number part of a, disregarding the sign, is smaller than 1, so we have a half or we have negative a half, in that case the parabola is going to be wider than the standard parabola. So this would be a vertical compression or a vertical shrink. Okay, so all of that from one variable. Can you believe that? All right, so then we take the other variables, the h and the k from this vertex form, go together to form the point that is the vertex. The vertex is the maximum or minimum point on the parabola. So if this were our parabola, this one is opening up, so the vertex is a minimum point. If it were opening down, then the vertex, of course, would be a maximum point. This is called the vertex, and then we have the axis of symmetry, because a parabolic shape is symmetric over the vertical line that passes through the vertex. So this vertical line down the center, because it's vertical, the equation for this line will be x equals some number. And all the points on this line will have h as their x value. So the x is fixed at the value for h. All right, so that's just some general information that we could use to talk about the parabola itself. Let's apply this now to an example. Let's analyze this graph. This is coming from your book in this section, number 23. So I think you can look at this graph and right away pick out the vertex. This time the parabola is opening down, so the vertex would be at this point here at the top. So that would be the point, -3, 2. And the axis of symmetry that divides the parabola in half would be here right down the center. There's a vertical line, x equals -3. Okay, and then we're just asking a few other questions to help us analyze what we see here. The domain for this graph. Remember, the domain for a graph runs from left to right, and the range runs from bottom to top. So if we look from left to right, there is no leftmost point. It's going to continue going left as it goes down. And so it's going to stretch all the way out eventually. Likewise, on this side, there's no rightmost point. It's going to continue. So all real numbers, -infinity to infinity for the domain. The range, because it's vertical, runs bottom to top. So there is no lowest point in this graph. It's going to continue on to -infinity. But as we go up, there is a highest point, and the highest point has a y value of 2. So the range goes from -infinity up to 2. There is a point there, so we want to include the 2, and we use the square bracket to show that. All right, then we want to talk about where the function is increasing and decreasing. So I am going up, the y values are going up. Remember, we make this judgment always from left to right. The y values are going up on the left-hand side of the graph until we get to the vertex, which has an x value of -3. Remember that we're going to describe the increasing and decreasing always with the x. So it's increasing from -infinity up to -3. This is the one where we said it really doesn't matter whether we decide to use the brackets or the parentheses. I'm going to stick with the parentheses this time. If you use the bracket, that would not be incorrect. That's totally fine in this case. Okay, decreasing as we go from left to right. The right-hand side of this graph shows the y values going down. So it's decreasing from an x value of -3 up to infinity. And then I think we can see that the vertex for this picture is a maximum. It's opening down, so the vertex is at the top. All right, so now you can talk about all those characteristics of a parabola. Now we want to be able to take a graph. We're going to use this same graph and write the equation for the graph that we see. It's just going to strengthen our relationship, our knowledge relationship with the graph and the equation. Okay, and we're going to start with the vertex form. We already identified the vertex on the last slide, so this is -3, 2. The vertex is h, k, so that means h must be -3. And k must be 2. This is totally in line with the shifting. It's moved left by 3 and up by 2. All of that is tied together. So we can start by writing the vertex form of the equation. We don't know a yet, so that's okay. We're going to leave a as a variable for the moment. So we have x minus h is -3 squared plus k, which is 2. So now we want to take what we have and use it to help us solve for a. So I want to use a point that is not the vertex and plug that in for x and y and use it to solve for a. So you could pick any other point except the vertex. I don't know which point looks the best to you. I'm going to pick this point right here, not for any good reason. Okay, So I'm going to use the point -2, 0. I'm going to plug the -2 in for x and the 0 in for y. So I have 0 equals a times -2. Really, this is a plus 3 because I have a double negative here, squared plus 2. The order of operations becomes really important when we do this part, so we really need to do the inside of the parentheses first. 3 plus -2 would be 1, and then squared would also be 1. So really this is like 1 times a, which is just a. It won't always be 1, so it is important to kind of think of it that way. And then we want to solve for a now, so we'll subtract our 2 over. And 1a is the same as a, so it looks like a must be -2. So let's write that in vertex form. I'm going to go ahead and make this x plus 3 squared again. All right, so we made the equation of that parabola. If we wanted to convert this into general form, we can just expand it out. So I won't ask for you to do that often, but let's go ahead and do it once so you can see it. So the square here means we're going to multiply x plus 3 by itself. And if I use FOIL to multiply these out, I should get x squared plus 6x plus 9. And then I would distribute my -2. So I'll come out with -2x squared minus 12x. This would be -18 plus 2 would be -16. So I found both the vertex form for this parabola and the general form. Okay, so you could find either format. If you're given a graph, you can find the equation. It's usually easier to start out with the vertex form and kind of work your way that way. All right, well, now let's talk some more about how to find the vertex. We can definitely use the shifting of the graph that we see to find the vertex. I didn't list that here. That's definitely an option. Okay, if the equation is not in vertex form, then we would either need to use completing the square or use what's called the vertex formula to calculate the vertex. Let's start out with the completing the square. This is described in your book on page 175, so please, if you need more information, definitely look in this section of the chapter. Okay, I'm going to summarize what's there. In this scenario, if we're doing completing the square, we're starting with the general form, which is this ax squared plus bx plus c. And we're going to convert it to the vertex form so that we can identify the vertex. So to do that conversion, we need to do that factoring, and that's where the completing the square comes in. So the steps we can take, and this is a little bit different than what I've seen in the past for the steps for this, so if you've already learned this a different way, by all means you can use your way. I like the way the book describes this because it's very consistent with how we would solve an equation using the completing the square method. So if you've done that, this is what might look familiar to you. The first step, we're going to divide both sides by a. This is going to allow us to have just x squared in the front. Then we're going to move the constant term. The constant term is just the number part, the c here. Maybe we've divided it by a, okay, but the number that's just here without a variable attached to it. So we're going to move that over to the left-hand side. These two steps are kind of interchangeable. So if you felt like it was easier to do the constant term and then divide, you could definitely do that. It would not change the process at all. All right, once we have done those two steps, we're going to be left with, I don't know if I can do this on the screen, but we're going to be left with x squared plus something x, okay? And so we want to take that and we want to add a number to both sides so that we're able to factor the right-hand side into a perfect square. Perfect square means we have two parentheses that are identical and that we can then write it as a square. Okay, and that's going to be in line with the vertex format that we've looked at already. Okay, to get it to look like a function again, the last step is to just isolate y. So we're going to kind of undo these first two steps so that we can make it back into a function. Okay, so let's try that out. This is number 29 from your book. So the first step is to divide both sides by 2. So we have y over 2 equals x squared minus 2x, plus 5/2. Okay, and for the completing the square process, I usually recommend keeping the fractions versus converting it to a decimal. It's still possible with a decimal, but usually the patterns that you're looking for are easier to identify if you leave it as a fraction. Okay, the next step is to move this is our constant term over to the left-hand side. So we'll have y over 2 minus 5 over 2 equals x squared minus 2x. Okay, and I should have left some space, I forgot. But the next step is to add a number to both sides. I always like to draw in a little blank here because I am pretty forgetful, and we're focusing a lot on the right-hand side, but we don't want to forget to add that same number to the left-hand side to keep things equal. Okay, so how do we decide on this number? There are a couple strategies that you can use. You can think ahead. The next step is going to be to factor this into 2 equal parentheses. So you can think ahead to what the factoring is going to have to look like and use that to figure out what the last number must be, kind of the idea of FOIL. Or there's a shortcut. So let me show you the factoring strategy first, and then we'll talk about the shortcut. So if I were to factor this into 2 equal parentheses, I know for sure I'm going to have x and x. Set it up that way to make it easier for myself. All right, and then I need 2 numbers in the back, 2 equal numbers that add up to the middle term, -2. These are always going to have the same sign as the middle term. Okay, so 2 equal numbers that add up to 2 must be -1 and -1. All right. And so I would get the last number here by using the idea of FOIL, the last times the last, -1 times -1. And this number is always going to be positive because the signs of these 2 parentheses are always going to be the same. And that's going to result in a positive number that we're adding. So we're going to add it here to make our factoring work out, and we're also going to add it here. Okay, so as a side note, the shortcut, we can use b over 2 squared. That is effectively what we just did here, right? We divided this by 2 to get 2 equal numbers. And then when we did the last times the last, we squared it. So that's a shortcut if you'd rather use that. I'm using the variable b because I'm talking about what's in front of the x. All right, keep in mind this is not the same as the b that we started with. We did some work, we divided it, okay. Technically it's b over a divided by 2, okay. So however you want to remember that, I think the book might list it as b over 2a. So if you would rather use that, then keep in mind that b would be the original b. I'm referring to this number right here. Okay, so -2 divided by 2 squared, this would be -1 squared. That's always going to be the number I have in my parentheses here before I square it. And so I get the same 1 that I would like to add to both sides. Okay, so that's the big step. That's the completing the square part. So now we would want to, we need to combine -5/2 and 1. So maybe you'd like to write this 1 as 2/2. This becomes x minus 1 squared. Okay, I didn't space this out very well. Sorry about that. So this will be y/2 minus 3/2. For the last step, I'm going to move the 3/2 back over here. So I'm adding 3/2 to both sides. And then I'm going to multiply everything by 2. So that's going to leave me with just y. 2 times x minus 1 squared plus 3. Okay, so I did the completing the square. Now, I wrote out a lot of steps here. You could probably condense this a lot. And if we do another example, I would definitely condense it a lot. I don't have another example in this video, but you could do several steps in your head, I think. Okay, I just wanted to give you a really full explanation. So from here, we could find the vertex, right? We could use the shifting in the h and the k. This one shifted to the right by 1 and up by 3. So h here would be 1, k here would be 3. So my vertex is the point 1, 3. All right, so that's the completing the square method. Now let's look at the vertex formula. I'm going to use the same problem so you can compare them side to side. So the vertex formula, and the derivation of this is in the book, I'm sure, but it basically takes this formula with all the variables in it and does the completing the square process. When it does that, the h part turns out to be minus b/2a. So there's also a formula for the y or value of the vertex or the k. It's usually easier just to take whatever you get for x and plug it into your function to find the y. So that's what we're going to do. Okay, so let's use that to find our x value. B here would be -4, so the opposite of -4 would be 4 over 2 times a, which is 2. So really that's 4 over 4. So the x value for this vertex is 1. And then if I take that 1 and plug it into my function, I'm going to have 2 minus 4, so -2 plus 5 would be 3. So my vertex is the point 1, 3. That definitely matches what we found in the previous method. Okay, let's add to that the graph. So the vertex would be the center point for the parabola, just because of its shape. So I would recommend putting that point in the center of your t-chart and choosing x values around 1. So a couple numbers smaller, a couple numbers bigger. And then we could plug those into our function. So if I plug in 0, I'm going to get 5. If I plug in -1, I'm going to have 2 plus 4, which would be 6, plus 5, which would be 11. All right. And if I plugged in 2, there's some symmetry here, so I should get 5. 2 times 4 would be 8, minus 8 plus 5, so that's 5. Likewise, if I plug in 3, I get 18 minus 12, that's 6 plus 5, that's 11. Okay, so if we plot those, I have the point 1, 3, 0, 5, -1, 11. Oh, I only went up to 9. I don't know why I did that, but okay, we'll put it up here. And then 2, 5, and 3, 11. It's been stretched vertically. So it looks sort of like this. Okay. So last, we have an application of this. This is sort of a baby step in the direction of physics. So we can use a quadratic function to talk about the height of an object that's been thrown into the air and gravity is pulling it to the earth. All right. So the A here is the acceleration due to gravity. If we use feet to measure the height, that's always going to be -16. If we use meters or something else, then that number will be different. But for now, we'll stick with feet. The coefficient for the x, or the t in this case, is the initial velocity or the starting speed. So if I throw it, whatever speed I throw it at would be that v0. If I drop it, I don't throw it, I don't put any force behind it, I just let go, then that would be 0. And then the initial height is, right, how high does this object start out? Okay, and of course it's measured in feet. So we could use this to talk about this toy rocket. This is number 66 from your book. It says a toy rocket is launched from the top of a 50-foot tall building at an initial velocity of 200 feet per second. The first step here, we want to express the height s as a function of time, t. Okay, I don't really like the s variable. I'd much rather use an h, but we're going with what the book has at this point. If you want to use h, that's okay with me. Okay, did you pick up on the things that we need? We have the acceleration due to gravity, so we have a. The v0 would be what? 200 feet per second. And the S0, or the starting height, would be this 50-foot tall building. Okay, we're going to launch it from the top of the building. So if we fill this in, S of t, or you could just use S, that's fine, would be -16 t squared plus 200t plus 50. Okay, now we're not going to graph this function, although you could on your calculator. You'd have to make an appropriate window. That could take some work, but you could do it. But in general, what is this? What is the shape of this graph going to look like? The t squared tells us it's a parabola, and the fact that the number here for a is negative means it's going to look like a parabola that opens down. Now, that doesn't necessarily mean that the toy rocket flew in the path of a parabola. It may have gone straight up and then straight down. But as time passes, the height went up It reached a maximum height, and then gravity took over, and it began to pull it down to Earth as time passed. Okay, so it may not have flown in this perfect parabola arc like it does on Angry Birds. All right. But as time passes, its height increased and then decreased. So the question then is, when will the rocket reach a maximum height? This is where the maximum height would be. This is the vertex. So we would like to find the coordinates for the vertex, the x value, and the y value. So to find the x, which in this problem is represented by t, we can use that minus b over 2a. Or we could do the completing the square, whichever looks the easiest to you. Okay, so this would be negative 200 over 2 times negative 16. If we punch that into our calculator, it should come out to 6.25 seconds. So it takes about 6 seconds after I launch the rocket for it to reach its maximum height. And then we want to know what is the maximum height. So we'll take this value for t and plug it in. Again, you can plug that into your calculator. It should come out to 675 feet. It is a good idea to list the units for the problem like this, just to make sure that you understand what the number is representing. Gives you a better feel for that. All right, well, I hope this gave you a good view of this idea of parabolas and quadratic functions. I think it would be really great to practice that, completing the square, and make sure that you can find the vertex as well. Good luck with this. See you in the next video.